Okay, so this is going to be, I want to see if I can do this all in one video, but I might, if it goes too long, put it into two. So let's get started here. 14.1. Okay, so we're talking about heat, and the first, a bunch of examples here are dealing with heat transfer. Um, I wanted to do this one as just a way to convert uh, between joules and calories. So basically, um, if we're given 500 food calories, which is actually 500 kilocalories. A calorie is a very small unit, um, so they make that approximation where, not approximation, but they make that thing where they just call 500, instead of saying, this food has 500,000 calories, they just say 500, but it means kilocalories. Okay, now the conversion is 1 calorie is 4.186 joules. Okay. Now the calorie is defined as the amount of heat or energy necessary to raise 1 gram or 1 cubic centimeter of water by 1 degree Celsius. But joules is the preferred metric or MKS physics unit to use. So we can also write 1 kilocalorie. It's 4186, 6 joules. Okay, so 500 kilocalories, basically times 4186 joules per calorie, joules per kilocalorie. I want to put the number here so we can look at it. Okay, so that's roughly 2,100,000 joules. Okay. Really just showing you how much energy is actually in food compared to mechanical energy, really, which is where joules mainly is used. Okay. Okay, 14.2. Now we're getting into the heat transfer equation. Q for heat, M C delta T. Mass, specific heat of the substance. Okay, where this one is going to be used a lot. I keep doing that. That's a 6 there. Joules per kilogram degrees Celsius. If you notice something here, that's the heat capacity for water. That's also how many joules in a kilocalorie. Okay, so let's just do an example here. So how much heat needed to raise the temperature of empty 20 kilogram vat made of iron from 10 to 90 degrees Celsius. Okay, so we'll just write everything down here, 20 kilograms. Okay, now I need to look up C for iron. It's right there on that page, 393. And we want to use the first column, 450 joules per kilogram degree Celsius. And then delta T, as always, is T2 minus T1. This could be a positive or negative. In this case, if we're rising temperature, so this is 90 minus 10. If it was going from, that's going from 10 to 90. If it was going from 90 to 10, then that would be negative 80. And then we just plug everything in. And I want to write this one out just so we get a good idea of what kind of numbers we're typically talking about with these problems. 20 kilograms is a lot of iron. So that's 720,000 joules. Okay, now what if it's filled with 20 kilograms of water? So iron plus water, so we have this amount of heat plus the amount that's going to go into the water. So all we need to do is do this again, but substitute in the heat capacity of water instead of iron, same degree change. Now if you notice here how much bigger the heat capacity for water is than iron, okay, and you think of heat capacity as the amount of energy it takes, or the amount of heat it takes to raise the temperature, by a degree, okay, so it takes a lot more energy to raise water by a degree than it does for iron for the same mass. But let's get an answer here. That's 6,700,000 joules. So a lot more. So total, you would just add those together. Okay, next one. 14.4. Okay, now this is a calorimetry problem, which basically where you're taking an unknown substance, changing its temperature by some amount, and then trying to calculate the either the unknown heat capacity of the substance, or if you know the heat capacity like you do for this problem, then you want to find sort of the equilibrium temperature. Okay, so calorimetry, you're always adding two substances together. Usually it's something like an unknown metal into water. It's the next example. Okay, this one's adding tea, so basically water, into a cup. Okay, so the calorimetry equation, I like using this version, that the sum of the heats, remember heat is an energy transfer, equals 0, meaning in this case it's hot tea, so the energy flowing out of the hot tea has to equal the energy flowing into the cup. Okay, and this way you don't have to worry about positives and negatives. Okay, so basically we can say Q, I'm just going to call the tea water from now on, plus the Q of the cup equals 0. MW, CW, delta TW, plus same thing for the cup. Okay, now you might think, how can this equal 0? Well, if the water is cooling down, then this is going to be, let's see, if the water is cooling down, then delta T here should be negative, and if the cup is heating up, then this one should be positive. So you do get a negative and a positive, and they're equal magnitude. But let's look at delta T again. Now I'm going to write it as T final minus T initial in this case. I think that's easier to follow. Okay, and just to solve this, because we're going to end up solving for TF, I'm going to move one of these to the other side. And I'll have to put a negative sign there. And then I'm going to expand the delta T's. So I'm going to have to say TF. Now I don't have to put a W there, but I do here. And I'll do the same thing. I'll explain that in a second. Okay. Because those are equal. Okay, they enter at different temperatures, but they equilibrize to the, it's not a word, but they equilibriumize to the same temperature. So I could put a W and a C, but then I would say those are equal, so we don't have to put the subscript. Okay, and then the next trick is just to bring this negative inside the parentheses there. These problems, just because there's a lot of variables, so they just switch places, right? You switch sign on both, and then you could write it like this. Okay, now let's see. We actually want to find. I'm going to calculate TF, and we know all the other stuff. So just in the interest of time, I'm going to let you do that. But basically, just to give you a heads up here, multiply through, because it just takes so long to write these things out. So I'll just do this first step here. Okay, now just get this term on the left and get this term on the right, and then factor out the TF on this side and then divide. So you'll get all these terms. This I can go ahead and write what we end up with here. If I can do this all in my head in one step, it doesn't really factor or have anything cancel out. So it would look like that. And you would just solve for TF. Now this is kind of the general formula for any of these calorimetry problems. But you might have a third. So I'll just to go to example 14.5 real quick, where we have an unknown metal. This is the unknown metal. Let me go back to this one. So if I had a third one, right? Let's say I had a spoon in the cup as well. It would just be, let's say it's a steel spoon, so I would have another term on the top and the bottom for steel, and then another term on the bottom here for steel. So you could just keep adding however many items you need there. Now 14.5, now we do have three objects. So the derivation takes that much longer, but we start again with our the sum of the heat equals 0, where now we have what they call a calorimeter cup, okay, which basically functions as the teacup, except it's like a thermos. It's designed to store, to not let any heat escape the entire system. And then we have the let me read this again. Alloy. Okay, they're using M for alloy. Sorry, they're using A for alloy there. So the heat transfer of the alloy plus the heat transfer of the water again. So the water's in the calorimeter cup at usually this is a hot temperature initial and this is a cold temperature initial, plus the calorimeter cup itself, which is aluminum. Okay. Now you're just going to do the same thing again. This will take me 20 minutes to go through, so I'm not going to do the whole thing. But you have to make this substitution, okay, for all the deltas, and then we're actually solving for the CA variable. Okay, so I'll let you work through that. Okay, let's see, 14.6. Okay, now we have, we're into the latent heat, so I'll just write that here, latent heat. Okay, and this is not heat that goes into a temperature change, it's the heat that goes into the phase change of the substance. Okay, so it has to be treated a little differently, because when you're, let's say you get water up to 100 degrees, so 100 degree water, Celsius, okay, and we say that's the boiling point, okay, but it doesn't all evaporate or boil at once. In In fact, if you turn the heat off, it'll stop boiling, right? So you got to put a certain amount of heat in that doesn't go to raising the temperature, but it goes to boiling, converting the water liquid to the gaseous phase, steam. Okay, and also you could do this for. So this is vaporization. Vaporization, whether it's boiling or condensing. So this way, from gas to liquid is also vaporization, or we call it that. It takes the same amount of heat, and then there's also melting. So if this is 0 degree ice, okay, to go from the ice to liquid takes energy, or to freeze it. So from liquid to ice, and this is fusion. So latent heat of vaporization for boiling or condensing, and latent heat of fusion for melting or freezing. And these are all on page 397. I'll write them here for water. And it's going to look like this. So LV, latent heat of vaporization for water, 2260 kilojoules. And LF, 333. You notice they're different sizes there. Okay, so the actual example here is we don't know how much energy does a freezer have to remove from 1.5 kilograms of water at 20 degrees C to make ice at negative 12 degrees C. Okay, so look where we're starting. We're starting at water, right? So when you're going past a phase change, you have to do this in stages. Okay, so stage 1, we're going to go water 20 degrees to 0. Stage 2, now we're freezing, right? So this is latent heat of fusion. And then for 3, we need the ice to go from 0 to negative 12. So these two phases are just what we did before. It's going to be Q equals MC delta T. C for water. Q equals MC delta T, where you're going to use the C for ice, okay, which I think is 2100. That's 20. Well, check the table for that. Now LF is a little bit different. So to calculate the latent heat of fusion, if you look, I should have wrote up here, this isn't kilojoules, this is kilojoules per kilogram, these heats, meaning for 1 kilogram of water or ice, it takes that much heat for 1 kilogram. So to calculate for different masses, it's just, the heat involved, it's just the mass times the latent heat of fusion or vaporization. Okay, so for this one, it's 1.5 kilograms of ice times, and it's fusion, so it's 333 kilojoules per kilogram. So we'll just call that 500 kilojoules for that phase. And then to get the total, you would just add them up. Okay, and one more here, 14.9. This is kind of a less important section here, really. This is, at least for this course, this is heating due to, or heat transfer due to radiation, just meaning any kind of light, any kind of electromagnetic radiation, so light, sunlight, infrared heating lamp, things like that. So we're going to use, now Q over T, that's actually a power rating, okay. Eta, the Greek eta, which is the emissivity. Okay, now that's basically how absorbing or reflecting an item is. Okay, so a very absorbing object, this is equal to 1, meaning it's the full value, and then it goes down to 0 for something that's completely reflective, times sigma, which is the Stefan-Boltzmann constant, the area, okay, that's emitting or absorbing, and then temperature to the fourth power. We don't have time to get into why that's a fourth power, but you know, it is, and that means this is very sensitive to temperature. This constant here, I'll write it out. Watts per meter squared Kelvin to the fourth. Okay, so any problem with this is going to be very straightforward. So this example 14.9, the athlete is sitting unclothed in a locker room. That just means at human temperature we emit infrared radiation. Okay. In the dark walls, meaning they're going to be absorbing. Okay. Dark walls are 15 C. Estimate the body's rate of heat loss by radiation, assuming a skin temperature of 34 degrees. And okay, so this is just a straightforward calculation. We have the emissivity, 0.7. I'm not going to write that out again. That's the constant right there. The area of the body. And then this T is actually it's kind of like a delta T. So you got to treat this as the temperatures in Kelvin. So I'm just going to go ahead and use those. Minus, since the body and this is the wall. See what's happening, and you can calculate this out, but what's happening is the body emits to the wall, but the wall also emits to the body. Okay? So while you're giving off heat basically to the wall is actually giving heat back to you, so you have to subtract off the wall there. Okay. Now, I want to go ahead and go through 15 because these examples are, I think they're pretty quick here. So, 15, now we're actually getting into thermodynamics and mainly focusing on this chapter and this topic, at least focusing on heat engines and what happens to sort of enclosed systems when you do work on them or add heat. So this guy right here is the first law of thermodynamics. U is the internal energy. So think about the internal energy basically as all the energy of all the molecules zooming around inside sort of a box of gas or something like that. Okay, so to change that, you can add heat. Okay, or you can do work on the system, which remember this negative here means we're defining work as work done by the system. So if the system does work, which means if it can expand, then that takes away from the change in internal energy. But if you do work on the system by compressing it, that's a negative, so it would be a negative of a negative. Okay, so think of delta U as anything that can heat up, raise the temperature of the system, needs to be positive here, and anything that can cool it down needs to end up as a negative over here. Okay. So 15.1, 2,500 joules of heat are added to the system. That should make the temperature go up, so we put that in as a positive. Okay. And 1,800 joules of work is done on the system. When we say work done on a system, basically that means compressing it. So the work here, we have to have negative 1,800. And then you just add them. Okay, the only trick here is recognizing the negative and positive there. So there's not really much calculation to do. You just end up adding them. 15.4. Now, this is such a big topic, and we can only really barely get into calculatable things without getting into calculus. And one of those is what they call an isobaric process. Okay, Isobaric refers to pressure. So if you're changing a system and you're keeping the pressure the same, okay, then the work we can define as that pressure times the change in volume. Okay, this is isothermal and this is isobaric, and it's really the only situation where we don't have to use integrals and stuff like that. Okay, so I don't want you to worry too much about, you know, all the ins and outs of all the different, like for example, I can show you this this graph here, where we're having a cycle where this is isovolumetric, meaning you're changing the pressure, and this is isothermal, you're letting it expand, keeping the same temperature, and then you're compressing it by keeping the same pressure, and we're only worried about this little leg here and not the whole thing, or you know what all that means. Okay, if you ever end up taking a 300 level thermodynamics class, you will do that. Okay, so basically, pressure is a constant, so whatever the pressure is, which they're telling us, if the pressure is 2 atmospheres, and this has to be in pascals, so we need to multiply that there. So this is just a conversion into pascals. Okay, and reading off of the graph, we go from, in terms of liters, so we'll say V1 is 10 liters and V2 is 2 liters. Sorry, 10 times 10 to the negative 3 meters cubed, and 2 times 10 to the negative 3 meters cubed. Yeah, we have to use pascals, meters cubed, and then we plug it in here. So pressure, I'll just use pascals, it's quicker there, and then volume, so V2 minus initial, and you notice this is going to give us a negative answer, which we do need because remember we defined work done by the system as positive, so if this was expanding we'd get a positive answer, but if it's compressing we get a negative answer. Okay, that's good on that one. Now let's do 15. I'm not going to go through 15.6 again because it's very similar to the latent heat question, and it'll just take too long. I don't think that's necessary for the homework or anything. So we'll get rid of that one. Let's go on to 15.8. On to a new topic here. Efficiency. So in terms of efficiency, just in general, think of it as work out divided by work in, or this could be energy out divided by energy in. So basically how much energy you're putting into a system versus how much work you're getting out. Okay, now that should be ideally 100%. Of course, in real life we never get to 100%. I think if we just see an example here, it'll make sense. Okay, so if we have this automobile engine has an efficiency of 20%, so that means E is 0.20, so we need to use decimals. Okay, produces an average of 23,000 joules of mechanical work. Produces, that means the output. Okay. And that's per second, but these things also go for power. We could have said power in over power out. How much heat input is required? So what is W in? And again, I guess technically we should write this as W out over Q in, just to be correct there. But these are all energies, right? So you can always substitute E, W, Q. Also power. Okay, so Qn is just the work out divided by E, so 23,000 joules divided by 0.2, and that's it. Whatever you get there. Well, let's get an answer here. It's multiplying by 5, so 115,000 joules. Okay. We're putting in 115,000 joules. We're getting useful work of 23,000 joules out. Now the difference there has to go somewhere else, and that always leaves the system as heat. So to get the amount of heat, you're just going to subtract the difference there. And whatever that is, that's the amount of heat that's discharged. Okay, 2 more here. 15.9. Now we get a special kind of heat engine called the Carnot engine. And this is sort of like the maximum efficiency that you could ever get out of the 2 temperature differences. Okay. Given by that, or also given by, if you cancel or write this differently, these are equivalent. I like using this one. Just lets me see better what's happening. So just anywhere it says maximum efficiency, you'll go to. You can't use, like we couldn't use this on the previous one because it didn't say maximum efficiency. Okay. So basically we have 2 temperatures. And these are all Kelvin. You need to use Kelvin here. Come on. Okay, and then just plug them in. I like to write it like this because it's the difference, right? It's the difference just in the temperatures over the hot temperature. So it's like, what percentage of the hot temperature does the difference make up? Okay, so this is going to be 230 K on the top over 773. And this is going to come out as 0.30, 30%. Okay, let's see, we got one more here. Get there. This last section is entropy. And it's kind of questionable whether to include that in at this level or not, because this is a very, very big generalization, and like the previous one, we can't really get into the depth of what entropy is at this level, but we can at least do one type of equation. It doesn't really tell us very much, but okay, basically this is very similar to the melting problem from before. So if we have the ice cube, mass 56 grams, starts at 0, and then half the mass melts. Find the change in entropy. Now, T, this has to happen at a constant temperature. Okay, so basically the part that melts, okay, so 56 grams, it's half of it, right? So $28. Okay, so 0.028 kilograms is melting. So the Q here is this latent heat of fusion. And this again is that 333 times 10 to the third joules per kilogram, and divide by put that there. Well, and then delta S is whatever this is over. Let's get an answer here. Okay, so that's 9324 joules divided by our temperature, which was 0 degrees Celsius, but that's 273 Kelvin. So divide by 273, and you get 34.2 joules per Kelvin. And basically, entropy is a measure of sort of the energy density as you compare it to temperature. And that goes up as you melt things and vaporize things. I guess that's really the best we can do in an explanation of entropy. Okay, that'll be it. I'll stop there.